A regression model can be very powerful, but the linear assumption is restrictive. What you can do is to see if transformation of some variables give better fits. Visually looking at the datasets, we can see that the relationship between y and x is not linear. So the linear fit does not give random residuals. If instead we use some transformation to make the model non-linear, as shown on the right side, then in the plot for the residuals, we can see that nonlinear fit gives random residuals. Plotting residuals is very useful for this purpose. Quadratic models may be considered when a scatter plot shows one of the following shapes. Note that beta 1 is the coefficient of the linear term and beta 2 is the coefficient of the square term. How can we test the effectiveness of the transformed model? There are several ways. We can compare f statistic with and without the quadratic term. We can run the standard coefficient test. We can also compare the adjusted or squared values. Let's look at an example. Consider the purity versus filter time dataset. The result looks okay, but if we run the test for the 5 assumptions, 2 assumptions are not satisfied. Here, one of the major reasons is the assumption for residuals is violated. Now let's add a quadratic term. We can see that the fit is even better. And the assumptions are all satisfied. You can also see the better fit with the residual plot. The dependent variable is never exactly a linear or quadratic function of the input variables. This is just because we are modeling reality. You can try a number of transformations such as taking a log or multiplying variables together. In general, there is no automated way to do this. Very often you need to guess and check or use some prior information or view the data. Now we talk about collinearity. Collinearity is the high correlation between 2 or more independent variables. This means there's some redundant information which can adversely affect the result. To detect collinearity, we can use variance inflationary factor or VIF. VIF j for the variable hj is defined as 1 divided by 1 minus rj squared. Rj squared is the coefficient of determination of the variable xj with all other x variables. If we got a value greater than 5, then we can say hj is highly correlated with the other independent variables. Let's look at an example. In this example, we train a model and later on use the VIF or VIF function to check VIF value. If the value is greater than 5 for at least one variable, then we eliminate the variable with the highest VIF value and rerun the VIF again iteratively. And eventually we end up with a model like this, which has 6 variables left. Given a regression model on k variables, you probably want to check if removing any variables would make the regression model better. The stepwise regression is a commonly used approach. We can add variables one by one until the regression model gets worse. Or we can delete variables one by one until the regression model gets worse. Or we can find the best possible subsets. In all, we use a function called step. So this is the algorithm. First, we decide on the input variables and the target variable. And we build a model with all the input variables. In step 3, we compute the width value for each independent variable. If we got no width value greater than 5, then this is actually very good. We go to step 4 to perform regression. If we have one width value greater than 5, then we eliminate the variable and go to step 4 to perform regression with the remaining variables. If we get more than one width value greater than 5, then we eliminate the variable with the highest width value and then go back to step 2 to redevelop a regression model. In step 5, we conduct an analysis to see if some transformations can make the model fit better. Note that we need to repeat steps 3 and 4 as well because we have new transformed variables in here.